guys. We're gonna do a short mini lecture on how we understand that climate's changed in the past, look at some of the evidence for that. And that's mostly on pages 399 to 402 in the textbook. And then we're gonna look at mass extinction events, which is the entire chapter 15, which I want you to look through. But in particular, I want you to focus on pages 437 to 440. So we can get that, so you make sure you get the key information that you need for this next little mini section. All right, so one of the ways we know climate has changed in the past is based on our geological records. So that's things like the fossils in the records, sedimentary deposits, the pattern of those sedimentary deposits. We use mud from the bottom of the oceans. We can use mud from the bottom of lakes. All of those things can contribute to how we reconstruct what's happened. And it's kind of like the scientists that work on these pieces go out and they take each of those different elements or the sort of lines of evidence and kind of create a story out of those pieces. There's also using ice cores, the vegetation records like pollen. We can also use historical records when they exist, so that's helpful in determining some of the changes and patterns that we've seen in the last few millennia, as well as instrumental records. So instruments, that's something that's really only been around in the last century or two, depending on where you are on the planet. So there's various tools we can go out there to collect that data and then be able to reconstruct what's happened. And that gives us a key to what the environment was like or what the climate was like at those times. And we'll talk about some of those records as we go through each of these lectures. But in particular, we're going to be thinking about the fossil record as we go through examples of mass extinction events. So mass extinction events, they're nasty. They usually involve rapid climate change or an initial event that then leads to rapid climate change. And sometimes, and we'll see this in the Permian extinction example, that we've got kind of like one big event, then created some chaos and some gradual climate change as well. And there's some important pieces to that. There's usually these things are related to things like volcanic activity, an extratropical or extraterrestrial impact event. And when we look at Earth's history, we see 6 major events. The 6 major events is the Ordovician, which is about 446 million years ago. And that was something that led to Southern Hemisphere continental glaciation. The Permian extinction was a combination of volcanoes and probably some global warming as well, or global climate change. There was a Triassic-Jurassic boundary, volcanic activity, and tectonics associated with the breakup of the megacontinent Pangaea. There was a Cretaceous tertiary extinction event at that boundary. That was an asteroid impact. There's also an extinction event 34 million years ago associated with plate tectonics known as the Eocene event. And then there's perhaps one that's ongoing now associated with a Pleistocene that may have started about 2 million years ago associated with an airburst. And there's evidence for that airburst over top of different parts of Siberia. So just focusing on the 2 big ones that I want us to talk about in our class is the Permian, which is 250 million years ago, as well as the Cretaceous tertiary or KT boundary. So number 2 and number 4 from our list on the slide. So the Permian extinction, this one was massive. This is the one that took out, I'm checking my notes here, took out 90% of the species that were living on Earth, and it took over 30 million years for life on land to recover. So this was catastrophic, to say the least. And again, part of the challenges associated with figuring out what happened is it was 250 million years ago. So our fossil records show us that abrupt change. We don't necessarily know what was happening on the day-to-day or even decade or century to century in this time frame. So we don't know how long that extinction event took place, but we're talking about kind of on the order of thousands of years. And there's some competing theories and some complementary theories about what caused this. And one of the ones that I think is most notable for us today is that deep within the northern oceans at the time, just north of where Siberia was, there was the seabed was essentially frozen methane or methane clathrates. And so as the ocean warmed up, those methane clathrates then begin to thaw. So if they're frozen, all that methane is trapped. And that's what this picture here is on the bottom left of our screen. That's frozen methane. And so as that starts to melt, you end up with that frozen methane then not being able to stay frozen, and it basically is a giant burp or fart, if you like, into the atmosphere of methane. So we have sort of the combination of initial events that's causing some warming. That warming made other things warmed up, and that led to a massive release of greenhouse gases into the atmosphere, which just sort of put that overall climate change and warming to the next level. And that's what sort of led to that massive, initially sort of gradual final phase or stage would have been catastrophic and really sudden. And again, might be a good analog for today. We still have frozen methane clathrates in parts of our northern oceans. We have lots of frozen methane just on the land, as we saw when we talked about permafrost landscapes a few weeks ago. So when we're thinking about what Earth might look like in a couple centuries from now, or hopefully not sooner, but a couple of centuries from now, we might see the release of some of those methane clathrates becoming a major issue. The next sort of big event that I want to talk about is the end of the Cretaceous, sometimes referred to as the KT boundary. So K for Cretaceous. I know that doesn't make sense, but in geological timescale worlds, that's what works out. That was about 65 million years ago, and 70% of all the genera on Earth disappeared. And this actually really set the stage for mammals. So before 65 million years ago, mammals didn't have a big role to play, but starting about 65 million years ago, mammals actually had some space, literally, to sort of start to evolve and become what they are today. So I think without the KT event 65 million years ago, we wouldn't have seen mammals the way we have them today. So probably not even us as part of that. Maybe, so who knows what we would have looked like. One of the things that's really interesting about the Cretaceous Tertiary event is the evidence that was there and how this got sorted out. So Walter and Louise Alvarez were looking at evaluating the amounts of iridium in different clay layers in some various areas. And iridium is something that's not found naturally on Earth, and so it's something that would only be transported to our Earth through a meteor impact, or a meteor hitting the Earth, impacting it. And one of the things they noticed in that clay layer was the fossils were drastically different above and below that clay layer that had all that iridium. So they sort of were like, something happened here, and it was a big deal. The problem was they couldn't find an impact crater to support this theory. So they published their paper in 1980, and then by the end of the 1980s, beginning of the 1990s, scientists had found a crater that sort of matched with the sort of expected magnitude and potential damage that we saw that led to the end of the Cretaceous and end of the dinosaurs, which was 65 million years ago. And that crater is in Mexico. It was hard to find because it's covered in tertiary deposits since then. So after Cretaceous ended, the sort of geological setting changed such that we ended up with a bunch of sediment accumulating in that crater. So it wasn't obvious on the landscape, and that's why they didn't see it right away. So this is a video, this is just to summarize the sort of climate proxies that help us to reconstruct what climate and environments were like in the past, some of the limitations and challenges associated with these. So things like figuring out how old our fossils all are, there's some dating uncertainties, as well as some conflicting evidence in some places. So what you might see in Northern Europe might differ than what you get in, say, South America, and trying to reconcile how those reconstructions might look different. The other challenge is that some proxies give us a ton of detail, but they don't go that far back in time. So think about tree rings. So tree rings give you each year a sort of an idea of what things were like for that tree, but we don't have trees that go back hundreds of thousands of years. And so we're sort of limited in terms of the details we can get and how far back in time we can go. Whereas there's some proxies that go way, way back, so hundreds of millions of years, but our resolution in terms of time, we're looking at things like maybe on the order of like plus or minus 10 million years would be a good range in some of those reconstructions. And then we talked about mass extinction events. And in particular, there's going to be questions on the quiz and the final exam that relate to those big events. So the Permian, those causes, and how that might work as an analogy for today's climate. And then as well as looking at some of the details associated with the KT boundary event. All right, guys, have a good day, and I will see you in the next video. Take care.